Area between two curves. Objectives. By the end of this lesson, you should be able to identify the region bound between two given curves, find points of intersection given two curves, algebraically and with a graphing calculator. When appropriate, set up an integral with respect to x that will yield the area between two curves, and understand when finding the area between two curves will require the setup of two separate integrals. Students should note that this lesson has a prerequisite of being able to graph any basic function by hand, including horizontal and vertical shifts to graphs, stretches, shrinks, and reflections. Basic functions include linear, quadratic, cubic, square root, cube root, exponential, logarithmic, rational, trigonometric, and absolute value functions. This lesson also has a prerequisite that students be able to find points of intersection on a calculator and use the store function, known as STO, on your calculator. So far, we have only been interested in the signed area between some function f of x and the x-axis. Well, now we're going to be interested in finding the area bounded between two or more different functions. So let's take a look at this graph right here. So I have two different functions represented. So let's go ahead and call this red function here f of x. And the blue function down here, let's call that g of x. So what we're going to be interested in finding, we're interested in finding the area that's bounded between these two functions on the interval from a to b. So I'm looking to find all of this area here. So we'll just kind of sketch it in for a quick second. So this is the area that I'm actually interested in finding. So now, how do we go about finding this area? Well, let's use some different colors here. What if I find the area bound between f of x and the x-axis? That's something I know how to do. So the area between a and b that's under the curve f of x, bound between f of x and the x-axis, is going to be all of this yellow area here. So let's say I find all of this area. So I'll try to shade it all in. Well, now, obviously, that's too much area. So I have all of the area that I want, but I have a little bit extra that I really don't need. So the idea would be to try to get rid of the area that I don't need. Well, that happens to be the area that's below, so strictly below, this blue function and bound by the x-axis. So again, I'm aiming for this black shaded region right here. Well, I know how to find the area under one curve and bound by the x-axis between a and b. That's all this yellow area. So that would be represented by the integral from a to b of f of x dx. But remember, that's too much. So I'm going to need to take away or subtract the area below the blue graph here called g of x. So if I find all of this yellow area and then I subtract this now green area here, so all of this area that's trapped between the x-axis and the blue function g of x, then I will have exactly what I'm looking for. So I will have exactly the area bound between the two functions f of x and g of x. So I need to write that as minus the integral from a to b of g of x dx. So now my properties of definite integrals say that I can combine these two to become one integral. So I'm solving the integral from, I'm going to write this as x equals a to x equals b, to remind ourselves that a and b are points along the x-axis, of the function f of x minus the function g of x with respect to the variable x. So if I want to find the area bounded between these two curves, well, another way I can write that is I can think about f of x was always the function on top, so this could be thought of as the integral from a to b of the top function minus the integral from a to b of the bottom function dx. So these are limits of integration that are x values, and I would have each of these functions be functions of x, and I'd be integrating with respect to x. So that's how we're going to find the area between two curves, is we're going to think of it as the top function minus the bottom function. But now the question is, how are we going to determine which function's on top and which function's on bottom? So sometimes that information will be given, sometimes it won't be. Now to look at the formula a little bit more formally for the area between two curves, provided that f of x is always greater than or equal to g of x for all x in the interval from a to b. So the formula is the integral from x equals a to x equals b of f of x minus g of x dx, or the integral from x equals a to x equals b of the top function minus the bottom function with respect to x. So the little side note here is that if the graph is not provided, we must draw a rough sketch to determine which function is on top and which function is on the bottom. If the functions alternate between top and bottom on the given interval, multiple integrals may be needed to find the area. And if an interval is not provided, we will have to algebraically or graphically determine the points of intersection to find the limits of integration. So this formula here that we took a look at using the previous example as well is the general idea, but we're going to need to go through quite a few examples to see all the different manipulations we're going to have to work through involving determining ourselves what the limits of integration are, determining ourselves what the top and bottom function is, and then possibly determining if we need to use more than one integral to find the total area enclosed between two different curves. So let's go ahead and take a look at some examples. Alright, so let's look at an example. So we're asked to find the area between y equals x squared minus 4x plus 10 and y equals 4x minus x squared on the interval from 1 to 3. So here, we've been given all the information we need. This is a very straightforward problem. So we've even been given the graphs here, although they're not labeled for us, but we should be able to figure out which one's which. So here we have a parabola, x squared minus 4x plus 10. So this has a y-intercept of 10, and it's a parabola that opens upwards. So this function here is going to correspond to x squared minus 4x plus 10. And that must mean that 4x minus x squared, so this is a parabola as well, but it opens downward, must be this blue graph here. So y equals 4x minus x squared is this second function here. So we are given an interval as well. Find the area between 1 and 3. So here's 1, so let's sort of sketch the area we're trying to find, and here's 3. So we're trying to find this area here that's trapped between these two curves and between 1 and 3. So let's go ahead and set up our integral. We're going to have the integral from x equals 1 to x equals 3 of the top function. So we have x squared minus 4x plus 10. So that's one whole function minus the bottom function, which was 4x minus x squared dx. So notice I was careful to include parentheses around each function because this negative or this minus between the two functions is going to need to distribute. So here I'm evaluating the integral from 1 to 3, so I'm going to lose the x equals. So now I'm going to have x squared minus 4x plus 10 minus 4x plus x squared dx. And this is the same as the integral from 1 to 3 of, I have two copies of x squared here, so 2x squared minus 8x, so I'm combining negative 4x and negative 4x, and then I only have one constant, so plus 10 dx. So now I'm evaluating a very straightforward definite integral, so I can use the power rule here and then use the Fundamental Theorem of Calculus part 1. So the antiderivative is 2x cubed over 3 minus 8x squared over 2 plus 10x evaluated from 1 to 3. So now, it's a lot of algebra, and we'll skip a little bit of it. So now, just to show the steps, what we would do is plug the 3 in for every x first. So we're going to have 2/3 3 cubed minus, let's write this as 4 times 3 squared plus 10 times 3. So that's substituting in just the 3 first, minus, now I get to substitute the 1 in everywhere, so minus 2/3 minus 4 plus 10. So doing a lot of algebra here, I would get a final answer of 16 over 3. And that's it. I've evaluated my first area between two curves given two functions, given the interval, and given the graphs of the functions. Now let's take a look at another example. So we want to find the area bounded by the curves y equals x squared minus 5x minus 7 and y equals x minus 12. So here we've been given our two functions. We've even been given the graph. So let's label which one's which. This aqua looking graph is the quadratic, so this one's going to be x squared minus 5x minus 7, and then the linear function must be x minus 12. So we've been given two functions, we've been given the graph, so we know which one's on top and which one's on the bottom, but we've been told to find the area bounded by the curves. So notice that these two curves actually intersect. So we're trying to find this area here enclosed by the two graphs. Notice what we're missing. We're missing limits of integration. So we have a top function, the purple graph, x minus 12. We have a bottom function, x squared minus 5x minus 7, for the region that we're trying to find the area of. But what we're missing are limits of integration. So those limits of integration have to be x values, since our functions are in terms of x. And we're looking at a top function minus a bottom function situation. So we want to set up an integral from x equals something to x equals something of the top function. The top function we said was the purple one, x minus 12. So the top function meaning of the region we're trying to find the area of. The bottom function is this aqua one. So x minus 12 minus x squared minus 5x minus 7 dx. So now, how do we find these limits of integration? So what I'm really looking for are points of intersection. What are the 2 points that this aqua graph intersects with this purple graph here? So more specifically, what are the x coordinates that this happens? So unfortunately, I can't just eyeball it. So I can't just go ahead and look up and say, well, it's going to happen at about 5 or 5 and estimate. I have to get exact answers here. So what I want to try to do is I want to set the two functions equal to each other and solve for x. So how do I know where these two things intersect? Well, that's where these two functions are equal to each other. So we're going to do some scratch work on the side. So I'm probably going to end up erasing this. Let's go ahead and set x squared minus 5x minus 7 equal to x minus 12. So I'm solving for x here. So let's go ahead and subtract x and add 12 to both sides. So I'll have x squared. If I subtract x, I'll have minus 6x. If I add 12, I'll have plus 5. So now I have a 0 on the right side. So this is a quadratic that I need to factor. So I'll end up with x minus 1, x minus 5. So if I solve, I get x equals 1 and x equals 5 as the two x values of my points of intersection. So the points of intersection are actually coordinate points, but I'm only concerned with the x coordinate because I'm going to take the definite integral with respect to x. So I found my two limits of integration. So the 5 we could see a little bit or make that educated guess, but again we want to be certain. And the 1, well, we wouldn't have been too sure there. So now we know that this was a 1 and this 5 does work. So our limits of integration are from 1 to 5. So now we have everything we need, and we just need to do some simplifying and then solve. So let's erase that for space. So this integral is going to become the integral from 1 to 5 of, here I'm going to have x minus 12 minus x squared plus 5x plus 7 dx. We'll combine like terms. So I'll have negative x squared. The x and the 5x will become 6x. And the negative 12 and plus 7, positive 7, are going to give us negative 5 dx. And so now I can take the antiderivative. I'm going to get negative x cubed over 3 plus, here I'll have, if I use the power rule, if I add 1, I'm going to get 6x squared over 2. So 6 divided by 2 is 3. So 3x squared minus 5x. And I need to evaluate this from 1 to 5. So now I'm going to go ahead and plug the 5 in. So I'll get negative 5 cubed over 3 plus 3 times 5 squared minus 5 times 5. And then I need to subtract, plugging in the 1. So I'll get negative 1 over 3 plus 3 times 1 squared minus 5. And, skipping the algebra, I end up getting 32 over 3. So the area here, you'll notice, is a positive area. So a couple things to mention about the area we just found bounded between these two curves. So first, if we're finding area bound between two curves, the area is always going to be positive, no matter where it's located, above or below the x-axis. The other thing I should mention is that in the first examples that we looked at, the functions that we were considering and the region we were looking at on the x-axis had functions that were entirely positive or above the x-axis. So our argument is actually okay to say that we're still going to do top minus bottom, even though now the functions are below the x-axis. So in this case, we said the top function was the purple graph and the bottom function was the aqua graph over the interval that these two functions intersected. So we can still use the top minus bottom argument even when the functions are located below the x-axis, but there is no more concept of negative area here, or our area bounded by curves is always going to be positive because we're just thinking about how much we can fit in between these two or three or multiple curves. So we did get out a positive number, and you might have asked yourself, well, why isn't it negative? Well, all area bounded by curves is going to be a positive number. Alright, in this next example, find the area bounded by the curves y equals 2 over x squared, y equals 2x, and y equals x. So this is a loaded question here because first the question is asking you to know the graphs of 2 over x squared, 2x, and x. We also don't have any limits of integration here, so we're going to have to find the points of intersection. So let's go ahead and draw ourselves a sketch of what's going on. So the first thing I'm going to do is I'm going to draw the two lines. So those should be jumping out at you as equations of lines. So y equals x being the most basic one. So let's go ahead and draw y equals x. So just the line through the origin with slope 1. So here's y equals x. Let's also go ahead and draw y equals 2x. So 2x is going to have a steeper slope, also going through the origin. So let's go ahead and draw 2x. So here's my function y equals 2x. And now it comes down to what does y equals 2 over x squared look like? So just a couple of reminders here. 1 over x looks like the reciprocal function. 1 over x squared, well, the first quadrant looks just like 1 over x, but in the second quadrant, I have another function that's going to be positive, or the other part of the function is positive. So this is 1 over x squared. Now, a 2 in front of a function does a vertical stretch by 2. So it's still going to have this form. It's just going to look a little bit more elongated here. So again, we're just drawing a rough sketch, enough to be able to find the region. So let's erase these two, and then we're going to draw 2 over x squared. So only in the first quadrant here. So let's go ahead and graph 2 over x squared. So we're trying to find the area of the region that's bounded by all of these curves. So these two lines and this curve. So the region bounded is this region right here. And it's kind of a tricky region. So let me go ahead and use the magic of making video lessons. And now here are our functions sketched out for us a little bit nicer. So here we have our functions. We have y equals x, we have y equals 2x, and the pink curve is y equals 2 over x squared. So we're interested in finding this area here that's trapped between these three curves. But something really unique happens. I have a different top and bottom function depending on where I'm at on the graph. So here I can see that I have a point of intersection. So 2x and x both start out at the origin. So I'm definitely going to start out at 0, and I'm accumulating all of this area here. And starting at 0, as I move along, the top function is 2x, the bottom function is x, and that stays the same up until right here, this point of intersection. And then now what happens is the pink function takes over as the top function. So this is actually going to have to be split into two separate integrals. So the first integral is going to be from x equals 0, so that's the first point of intersection, to we have to solve for this point of intersection. So I want to find where does the blue graph intersect with the pink graph. So it looks like it happens at 1, but again, we would have had our little rough sketch, so that rough sketch probably wouldn't have told us exactly where it would happen. So what would we do? We would set the pink graph, 2 over x squared. We would set that equal to the blue graph, 2x, and we would try to figure out what x value solves this. So let's multiply both sides by x squared. I'd have 2 equals 2x cubed, and that's 1 equals x cubed if I divide both sides by 2. And the only thing that's going to solve this is x equals 1. So x equals 1 is the correct upper limit of integration for the first integral. That's going to give me just this area here. So let's erase that. That was the scratch work really for finding the other limit of integration. And then we do top minus bottom. So top being 2x minus the bottom function is just x dx. So now I've only found this portion of the area bounded by the curve. So I have to find this part too. Well, this part's going to pick up at 1. So we're going to be having an additional integral. So plus the integral from x equals 1 to x equals, we're not sure yet. That's going to happen at whatever this point is here. So we have to keep going, and we're going to add all this area from 1 to this point of intersection. So we have to find that value. And then the top function is now going to be the pink one, so 2 over x squared, minus the bottom function is still the line y equals x dx. So now we need to find this point here. So we need to find where does the pink graph, 2 over x squared, where does that intersect with the green graph, which is just x. So if I multiply both sides by x squared, this will cancel. I'll get 2 equals x cubed. So to solve for x, I need to take the cube root of both sides. So x is the cube root of 2. So x is the cube root of 2. So that's my other limit of integration here. So now I've set up the integrals required for me to find the area that's bound by these three curves. So let's simplify the one on the left. So we're going to do the integral from 0 to 1 of x dx, that's a nice one to solve, plus the integral from 1 to radical 3 over 2. I'll write this as 2x to the negative 2 minus x dx. So now this one, we're going to get x squared over 2, evaluated from 0 to 1, plus this one's going to be 2x to the, if I add 1, I'm going to have negative 1, and then I'll divide by the negative, so there's a minus here, minus x squared over 2, evaluated from 1 to the cube root of 2. So evaluating this first integral is going to be nice, so we'll just plug in the 1. So we'll get 1 squared, so 1 over 2, and if I plug in 0, I'll get 0 over 2. So 1/2 is the first integral. And then here, well, this one's going to look pretty ugly. It's going to be negative 2 over the cube root of 2 minus the cube root of 2 squared over 2. And that's just plugging in the cube root of 2, and then I subtract plugging in 1. So I'll get negative 2 over 1 minus 1 over 2. And let's see if there's really any simplifying we can do here. We have this 1/2, the negative 2 over 3 rad 2, not much we can do there. Not much we can do to this, the cube root of 2 squared over 2. Here, though, what do we have? So we have negative 2 minus 1/2. So if we add the opposite, we have negative 2 minus 1/2, so we have negative 5/2, but this plus will make it plus 5/2. So 5/2 and 1/2 gives me 3. Can't really do too much with it. 3 minus 2, the cube root of, over the cube root of 2 minus the cube root of 2 squared over 2. And if this was a graphing calculator problem, we can go ahead and plug that into our calculator, but this is really all the simplifying we'd need to do. We'd never try to approximate a cube root number. We would never approximate pi either, so if we had pi in our answer, we would just leave pi in our answer. So the hard part here is setting up the integral. And in fact, some AP questions will just have you set up the integral, and that's the entire problem. Because the rest of this is a lot of algebra, and they wouldn't really want you to lose a point messing up on some trivial algebra when you knew the calculus. So the calculus is setting up the integral and understanding that this particular area bounded by curves requires the setup of two separate integrals because the top function changes. So the top function starts out as 2x and then changes to 2 over x squared. Alright, now let's go through some assorted AP multiple choice questions. So number 15 of a previous exam asks you to find the area of the region bounded by the lines x equals 0, x equals 2, and y equals 0, and the curve y equals e to the x over 2. So x equals 0, x equals 2, and y equals 0. Let's graph all of those first. So y equals 0 is just the x-axis. So I know that the x-axis, switch to a different color, I know that the x-axis is going to be one of the bounds. And now x equals 0, well that's the y-axis, so that's going to be another bound. X equals 2 is going to be yet another. And then finally, graphing y equals e to the x over 2. So first let's think about the parent function for a second. So if I have y equals e to the x, so rough sketch e to the x goes through the point 0, 1. So here's what e to the, whoops I missed, but here's what e to the x looks like as a rough sketch. So when I have 1/2 in front of the x, what does it do? So when I change this to 1 over 2x, when I put a number in front of the x variable, it's going to give me a horizontal, either a stretch or a shrink. So a 1/2 in front of the x, since that number is between 0 and 1, the number 1/2 is going to give me a horizontal stretch by the reciprocal of this number by 2. So a horizontal stretch by 2, it's going to make this thing go a little bit wider out. So I'm thinking about horizontal meaning like the horizon left to right, so I'm stretching it out, so kind of making it wider a little bit, but this point is still going to stay the same, so it's still going to go through 0, 1, just going to look a little bit wider. So if you don't remember the exact details, even knowing what the graph of e to the x wouldn't steer you wrong in this problem. So e to the x goes through 0, 1, so let's go ahead and draw a sketch of it. So here we're going to draw that sketch of e to the x over 2. We'll say it's a little bit wider than the regular e to the x graph, but they're pretty similar and it's close enough for our sketch. So we want to find the region that's bound by all of these lines here and the curve. So we want this, the area of this region here. That's what we're looking for. So there's a clear top function. The top function is e to the x over 2. The bottom function, it's a boring one. It's 0. So this horizontal line here is y equals 0. This function here is y equals e to the x over 2. And we actually do have limits of integration that are x values. We have x equals 0 and x equals 2. So we're evaluating the integral from x equals 0 to x equals 2 of the top function e to the x over 2 minus the bottom function 0 dx. So let's go ahead and shorten this to the integral from 0 to 2 of e to the 1 over 2 x dx. So now this antiderivative here, well, it's going to be e to the 1 over 2x times 1 over 1 over 2, which is just 2, evaluated from 0 to 2. So let's go ahead and substitute in 2. So we have 2e to the, if I plug in 2 for this x, 1/2 times 2 is 1, so 2e to the 1, minus, if I substitute in 0, I'll have 2e to the 0. E to the 0 is 1, so I really have 2e minus 2. So if I look at my options, I don't have exactly 2e minus 2, but if I factor out a 2, I do have 2 times the quantity e minus 1. So my answer here is C. Alright, another multiple choice AP question, 17 from a previous exam. What is the area of the region completely bounded by the curve y equals negative x squared plus x minus 6 and the line y equals 4? So let's go ahead and start with a rough sketch again. So here's my xy axis. Let's first draw the easy function, y equals 4. So this is a horizontal line at 4. So let's go ahead and draw that. And now I want to try to sketch negative x squared plus x plus 6. So first of all, this is a parabola because this is a quadratic function. The negative in front of the x squared term means it's going to open downward, and the plus 6 means it's going to have a y-intercept of 6. So I don't know exactly what it's going to look like. I know that a point on the curve goes through 0, 6. So my curve might look something like this, or it could even have looked like this. I'm not entirely sure what it's going to look like. Let's say it looks like the first one that I drew. But either way, it's a good enough sketch to determine which function would be on top and which function would be on the bottom. So the function that would be on top would be the quadratic, and the linear function, the constant, would be on the bottom. But we're missing our limits of integration, so we need to find the points of intersection. So to do that here, this would be a non-calculator problem. We would need to set the curve negative x squared plus x plus 6. We would need to set the curve equal to the other equation here, so y equals 4, and solve for x. So here, we'll go ahead and add everything to the right side, so we end up having a positive x squared. So we're going to end up with 0 equals, if I add x squared to the other side, I'll have x squared. If I subtract x, I'll have minus x. And if I subtract 6, and I have a positive 4, I'll have minus 2. So let's go ahead and factor this. So I have x minus 2, x plus 1 equals 0. So x equals positive 2 and negative 1. So that looks pretty good based on the sketch that I drew, that the x value of the point of intersection on the left is negative 1 and on the right is positive 2. So now I have limits of integration, so I can set up the integral. So the integral is going to be from x equals negative 1 to 2 of the top function, negative x squared plus x plus 6 minus the bottom function 4 dx. So this is the integral from negative 1 to 2 of negative x squared plus x plus 2 dx. And now this is negative x cubed over 3 plus x squared over 2 plus 2x evaluated from negative 1 to 2. So in this problem, they are going to make you do a whole lot of algebra here. So we can tell from our answers that we're going to end up with a fraction. So let's plug in 2 first. So if I plug in 2, I'll get 2 cubed, that's 8. So I'm going to get negative 8 over 3 plus, if I plug in 2, I'm going to get 2 squared, so 4 over 2 plus, and here if I plug in 2, I'm going to get 4. So now, minus, now if I plug in negative 1, I'm going to have negative 1 cubed is negative times another negative is positive, so minus 1/3. If I plug in negative 1 and square it, I'll get a positive, so plus 1/2. If I plug in negative 1, I'll get minus 2. So now this negative here would distribute. I'm running out of space here. So we're going to have negative 8 over 3 plus 4 over 2 is 2 plus 4 minus 1/3 minus 1/2, so I'm distributing in this negative, plus 2. So let's see what's going on. I have 2 plus 2 is 4 plus 4 is 8. So I have 8. I have negative 8/3 and negative 1/3, so that's negative 9/3. And then I have minus 1/2. So 9/3 is 3. So I have 8 minus 3 minus 1/2. So I have 5 minus 1/2. So that's going to be 4.5, which as a fraction, because my answers are fractions, is 9 over 2. So the answer here is C. And if you've been looking at our multiple choice questions from AP exams, it looks like the answer is always C. And I'm not sure why I conveniently keep picking those, but please don't just mark C on every single question on the AP exam. So this is the 2008 AP Calculus BC free response question. And this problem here did require the use of a graphing calculator. So here's the given graph, and the question states that we're going to let R be the region bounded by the graphs of y equals sine pi x and y equals x cubed minus 4x as shown in the figure above. Part A. Find the area of R. So here's what we're going to want to do. Even though this is a calculator-based question, we can use our calculator to find the answer. You want to get points for the setup, because if you accidentally enter something wrong into your calculator and you just write down a wrong answer, they can't give you any credit at all for that. But if you show the setup, there's points involved in the setup of the problem. So depending on the problem, points are given throughout different parts of what you set up. So let's go ahead and set up an integral here. So here we have this region R. It's been shaded in for us. The graphs have been given. It's a graphing calculator problem. If you didn't know which one was which, if you didn't know that this top one here is the sine one, so this function here is y equals sine pi x, and then the bottom function here, that one is x cubed minus 4x. If you didn't know that, it's a graphing calculator problem. So you can plug them into your graphing calculator and know which one's which, but hopefully you would know which one's which. So even now, so if you think about substituting 1 into both of these functions, well, if you substitute 1 into x cubed minus 4x, you're going to get 1 minus 4, or negative 3. So that matches up down here with this coordinate point. So just plugging in values, you would know which one's which. But again, it is a graphing calculator problem. So top one, sine pi x, bottom one, x cubed minus 4x. So the integral we're going to set up here is the integral from x equals, we need limits of integration. So here, they've made it clear for us that the two functions intersect at 0 and 2. So our limits of integration are going to be x equals 0 and x equals 2 of the top function, so sine pi x, minus the bottom function, and we'll put that in parentheses, x cubed minus 4x dx. So let's go ahead and actually try to use our graphing calculator to get the exact answer here. So some practice with the graphing calculator. Alright, so let's go ahead and try to evaluate this here. So we're going to go to Math 9 for integration, and our limits of integration were 0 and 2, and our integrand was sine of pi x minus, and here we'd want to use parentheses because our function was x cubed minus 4x. And then our differential was dx. So if we go ahead and solve this, we get exactly 4 out as our answer. So let's come back here and write our final answer as 4. And that's the answer to part A. So now let's go ahead and try to solve part B. The horizontal line y equals negative 2 splits the region R into two parts. Write, but do not evaluate, an integral expression for the area of the part of R that is below this horizontal line. So let's go ahead and construct the horizontal line y equals negative 2. So horizontal line at y equals negative 2 splits the region into two parts. So we're interested in finding the area of the part of R below this line. So we're interested in finding this area here. So remember that this line is y equals negative 2. So what we're interested in finding is the area of top minus bottom. So all we're missing is limits of integration. So we need to find these two x coordinates. So x equals something, and then this point up here is x equals something, and that's what we need to find to finish the setup of our integral. So it's going to be the integral from some number to some number of the top function's negative 2, minus the bottom function. So the bottom function here is the cubic function, So I have minus the quantity x cubed minus 4x dx. So all I'm missing here is my limits of integration, and for that we are going to need to use our graphing calculator. So we're going to go through the process of finding points of intersection on our graphing calculator next. Alright, so let's go through the process of finding points of intersection using our graphing calculator. So we're going to go to y equals, and we're going to enter our two functions. I'm going to go ahead and put -2 first, and then I'm going to enter the cubic function x cubed minus 4x. And then I'm going to go ahead and graph. So there's y equals -2, and there's my cubic function. So remember, this little region right here is the one I'm interested in. So let's go ahead and zoom in on that. So I'm going to go ahead and go to zoom in, and then I'm going to move my little cursor using the right and down buttons to maybe right in the middle of that region, and then I'm going to hit enter. So now I'm zoomed in enough to where I can see more clearly the region I'm trying to find and those points of intersection that I'm trying to find. So to find points of intersection, we're going to go to second calc, or second trace for calculate. Then I'm going to go down to 5 for intersect. And now, to find points of intersection, we're going to find this left point of intersection first. So the calculator is asking me, are you on the first curve where you want to be? So are you close to the point of intersection you're trying to find? So in the top left corner, it's telling me I'm on the function y1, which I set to be -2. And now I'm moving it over so it's close to the point of intersection. So first curve, are you close to the point you're trying to find? Yes. So then hit enter. Now it's telling me in the top left I've moved down to the cubic function, and I'm still close to the point of intersection I'm trying to find, so I just can go ahead and hit enter again. And when it says guess, I can just go ahead and hit enter again. Alright, so now I found that the x value of the point of intersection is happening at 0.5392. Alright, so this problem in particular only wanted us to set up the integral, but we're going to go a little further and we're going to solve the integral. And in fact, we're going to learn how to store variables right now. So let's say this number didn't terminate. So right now it stops at 0.5392, but if it just kept going on, we would never ever want to stop and approximate this value, because then we're using an approximation to find an approximation of the area between two curves, and that's going to get us further away from the correct answer. So how do we avoid that? We store this number. So right now, temporarily, this number 0.5392 is being stored in the calculator under the variable x. That's a really bad place for it to be, because we constantly use x all the time for different functions. So we want to store this number into a different variable. So what we need to do is be very careful. So once we see this is the point of intersection, we're going to go back to the home screen. So we're going to go second quit. So now here's my home screen, and the first thing I want to press is store. So I'm going to press the store button. And what it's saying is that your previous answer, which it was holding as that x value of the point of intersection, this little arrow is saying, where do you want to put that? So I'm going to tell it to go to A. So I'm going to go ahead and hit alpha A. Enter. So now, anytime I want to go back and reference that number, 0.5392, I can just hit alpha A. Enter. There's my number. So 0.5392 is stored under the variable A. So now let's go back to the graph, because that was only one of the points of intersection we try to find. So repeat the process. We're going to go to second trace for calculate, 5 for intersect. Now I'm going to move on over to the other point of intersection using the right arrow button. Hit enter because I'm close to it. Now I'm on the curve, and I'm still close to the point, so I'll hit enter again and enter again. So now I found that the second point of intersection is 1.6751. And we're going to want to store that number as well. So we're going to go straight to second quit. We're going to choose store, and let's go ahead and store it under alpha B. enter. So now anytime I choose B is holding that number 1.6751 until I change it to something else, or I go into the memory and I change it myself. So right now A and B are specific numbers, these two numbers respectively, the points of intersection. So if I wanted to actually evaluate the integral, and I'm going to go one step further than I actually need to here, just to show how to do it, I want to set up the integral from A to B. So let's go to Math 9. And instead of typing in numbers, instead of typing in 0.5392 and 1.6751, I'm going to go ahead and type in alpha A to alpha B of the top function, which we said was -2, minus the bottom function, which we had as x cubed minus 4x dx. And if I go ahead and hit enter, I found that the answer is 0.8114. So I can see right now my calculator is on a setting that just terminates the decimals at 4. So in fact, these numbers, I'm sure, do go on and on. So we would be using approximations if we just entered in these numbers exactly. So I have to go into my mode and change it, because right now I could tell my calculator is just cutting me off at 4 every single time. So this here would be the answer to the actual definite integral, but the problem was only asking me to set up the integral. So let's go back and set up the integral the way we would need to for the exam. Alright, so the last thing we're going to do here is we're going to come back and we're going to put the limits of integration in. So if we want, we can go ahead and write A to B, but the AP reader is going to have no idea what you're talking about unless you actually put values somewhere on your page that represent A and B. So I should go ahead and write that our value for A was 0.5392 and our value for B was 1.6751. So I never want to use a rounded number at any step until the last answer. So the last answer, we can go ahead and cut it off after 3 decimal places, or round to 3 decimal places. But any intermediate value that I want to use, I want to store it using the process that we just went through right now. To store each of those numbers, and then the final answer is the only thing that I would actually want to round or truncate. So here, since these limits of integration are part of your final answer, as long as you're right up to 3 decimal places on each of these limits of integration, your answer to part B is correct. So now we're done with parts A and B of this problem. There are actually 2 other parts to this problem, C and D, but we haven't gone through the methods to solve them yet. So we'll come back to those portions at a later time, but so far we've gone through half of this free response question.